Hello, my name is Tim Blackmore and I'm presenting the paper Novelty-Driven Verification using machine learning to identify novel stimuli and close coverage at DVCon U.S. 2021. My co-authors are Reese Hodson, who works with me at Infineon Technologies Bristol Design Centre in the UK, and Sebastian Schall, who is co-founder of Luminovo, based in Munich, Germany. I'll start with an overview of the key points of the presentation. The presentation is about an application of machine learning to improve the efficiency of the verification of a real-world design. So we start with a description of the design and of its verification, and we describe why we believed the verification could benefit from the use of machine learning. We go on to describe the type of machine learning we used and why. This wasn't the supervised machine learning that people are probably most familiar with. This didn't seem well suited to our application. Instead, we used unsupervised machine learning algorithms aimed at identifying novelty in tests. Before using machine learning on an executing project, we ran a significant experiment. This was based on a large database of tests and of their simulation results. We described the experiment and the results of the experiment. We finished with a conclusion and some suggestions for future work. So we begin with an overview of the design and of its verification. The design is a radar signal processing unit, which we call the RSPU. It's used in automotive radar applications, in particular in advanced driver system or ADAS applications and level 2+ self-driving applications. The RSPU consists of a number of processing units that together form a processing pipeline. Each of these units is configurable, and overall the RSPU has over 300 configuration fields, most of which are many valued. Radar data is streamed through the pipeline, and the processed data is written to memory. The RSPU can then reconfigure itself, fetch the processed data from memory, and process it again. This, for example, can be used to calculate the relative velocity or the angle of arrival of an object on the road. The tests used in the verification of the RSPU consist of a configuration of the RSPU and of radar data. The radar data can be either driven into the front end of the RSPU or placed in memory for the RSPU to fetch. This means several tests can be run back-to-back to emulate the reprocessing of data. The test generation is automated using constrained random generation. To identify when a generated test has done something of interest, we have an extensive functional coverage model. The coverage model is split between configuration coverage and white box coverage. Configuration coverage consists of all the interesting configurations identified by all the various stakeholders. The configuration coverage is black box because we do not need internal probing of the RSPU to know how it is configured by a test. This can be decoded directly from the bus interface of the RSPU or even taken directly from the test. The white box coverage, however, does require internal probing. It is focused on the activity in the design, both within and between the processing units. In particular, it looks at identified corner cases in the design. So simple examples of white box coverage would be a FIFO being full or a processing unit seeing a particular input when a state machine is in a particular state. Our focus is on the configuration part of the test and on the white box coverage part of the coverage model. We focus on the configuration part of the test because the design behavior is much more dependent on how the design is configured than it is on the data that is processed. We focus on the white box coverage because this is the coverage that is hardest to close. The relationship between configuration and white box coverage is indirect and not easily determined. Whilst it is quite easy, if necessary, to constrain a test to hit configuration coverage, it requires much more effort to write constraints to target white box coverage that is not hit randomly. The verification environment for the RSPU is a little unusual in that the constrained random generation of the tests is completely decoupled from the simulation. So instead of generating stimuli and passing it to a driver a transaction at a time, we generate a full test before we pass it to the simulation environment. The generated test is written to a database of tests before being accessed by the simulation environment. This, of course, means that there is no feedback from the design during generation. Any design-dependent test bench behavior is instead taken care of by the driver. So, for example, if the test bench needed to react to an error response from the design or to an interrupt request, this reaction would be pre-generated and selected by the driver when necessary. Although the decoupling of generation in simulation is not common, it has a number of advantages. The reason we first introduced it was to avoid random instability. We found that we were having to make frequent changes to our generator, and having to regenerate tests across these changes was making coverage closure difficult. Having the tests saved in a database made the regeneration unnecessary. This approach has also enabled us to use different languages for our generation and for our simulation environments. So our generation is done in SpecMini and our simulation is in System Verilog, which is a mix that we like well. Another benefit is that the tests in the database can be easily ported from IP verification to subsystem or SSE verification, or even to FPGA or post-silicon environments. Essentially, we have a basic form of portable stimulus. Finally, and most importantly for this presentation, this allows for generated tests to undergo some post-processing before being passed on to the simulation environment. This has a number of benefits, but the most important in the context of this presentation is that it means that some generated tests can be filtered out before being simulated. We finish this part of the presentation with a look at some of the verification numbers. Firstly, we note that the cost of not simulating a generated test is small because the simulation time is much greater than the generation time. 2 hours on average for simulation compared to around 5 seconds for generation. Next, we note that closing coverage on the RSPU typically requires simulating around 2 million tests. And the most time-consuming part of this is hitting the 6,000 or so white box coverage bins. Using around 1,000 machines and licenses almost continuously, simulating these 2 million tests takes about 6 months. During this 6 months, we produce a ranked regression, which contains an optimized set of tests for hitting all of our coverage. Of the 2 million simulated tests, this ranked regression contains only around 3,000 tests. This indicates that there is a lot of coverage redundancy in our simulated tests, with many tests hitting the same coverage over and over again, but hitting no new coverage. We now move on to looking at the type of machine learning we used. Here we've divided computer algorithms into traditional algorithms and machine learning algorithms. With traditional algorithms, you write a function, pass it some input data, and it gives you the input data with the function applied as output data. This works perfectly well when the function between input and output data is reasonably easy to describe, but for many applications this is not the case, which is where machine learning comes in. In machine learning, the machine is trying to learn a function. The most common form of machine learning is supervised machine learning. This depends on the existence of many known input-output pairs. For these known pairs, the output is called a label for the input. A machine learning algorithm learns a function that recreates the input-output pairs. This function can then be used to predict outputs for new unlabeled inputs. Sometimes no labeled data exists. In this case, it can still be possible to find patterns in the input data, and algorithms that do this in an automated way are called unsupervised machine learning. The types of functions they learn are how the input data clusters, or what typical input data looks like, or indeed what anomalous or novel input data looks like. Our goal is to reduce the redundancy in our set of simulated tests so that we can close coverage more quickly. Our target would be to reduce the 2 million tests we currently need to simulate to close coverage down to 1 million or fewer. With the aim of reducing the number of tests that we simulate, we introduce a test selector between our generation environment and our simulation environment. This selector would look at a generated test and only pass it on to the simulation environment if it considered that the test may add to coverage. As we've already said, the relationship between a test and its white box coverage is not easily described, so the use of traditional algorithms for the test selector isn't feasible. We could label simulated tests with their coverage and use this labeled data to train a supervised machine learning algorithm to predict the coverage achieved by a newly generated test. However, we will never have any simulated tests labeled as hitting coverage that has not yet been hit. So a supervised machine learning algorithm may be able to predict that a test will do well at hitting coverage that has already been hit, but will not be able to confidently predict that a test will help with coverage closure. So such predictive algorithms don't seem well suited for our test selector either. However, unsupervised machine learning doesn't try to make such precise predictions. A test selector based on unsupervised machine learning would look only at the generated test and could select tests based on how novel they look compared to the tests already simulated. We would hope this novelty correlated to hitting new coverage. It is worth noting that we are not expecting an exact correlation between novelty and coverage closure. We are looking only to reduce redundancy, not remove it altogether. It is of course useful to have a certain level of redundancy in our set of simulated tests, since our coverage model will not be perfect and there may be bugs that are exposed by scenarios that we do not have coverage for. Now we look a little at the type of unsupervised learning we used. It is a type of artificial neural network called an autoencoder. So it consists of connected layers of neurons, but it is unusual in that the output layer tries to reconstruct the input layer. It can be used to encode an input into a compressed form in the central layer and to decode it again. It is trained to minimize the total loss between the input and the decoded output. In this way, it achieves an optimum encoding in the central layer. We note that, although an autoencoder is a neural network, it implements unsupervised machine learning, since the labeled outputs are just the inputs. From these inputs, the autoencoder learns two functions, an encoding function and a decoding function. Once trained, an autoencoder works well at encoding and decoding data, similar to the data it was trained on. For such data, the total loss is small. However, the total loss is likely to be bigger for very different looking data. In this way, the total loss can be regarded as a measure of novelty. In our case, the autoencoder would be trained with the simulated tests. It would then be used to select a new batch of tests to simulate. As well as being simulated, these tests would be added to the training set for the autoencoder and the autoencoder retrained. In our case, the feature set used as the input to the autoencoder are just the values of the configuration fields generated as part of the test. These fields may be categorical or they may be ordinal, but a really nice aspect of using an autoencoder is that it does not depend on any measure of distance in the input space. We can just encode our configuration fields as one-hot vectors, pass the vectors to the autoencoder, and let it do its work. We now describe our experiment. To run the experiment, we saved just over 85 tests, along with the coverage that they hit, to a test coverage database. The tests consisted of the 3,000 ranked tests that give 100% coverage, and 82,500 randomly generated tests that were simulated across a week and 2 weekends. Saving the tests and their coverage to a database allowed us to quickly generate coverage closure curves when simulating these tests in different orders. So, for example, we could compare coverage closure when the tests were ordered according to novelty, with coverage closure for a random ordering of the tests. For the novelty ordering, the autoencoder is used to select the tests that were most novel, compared with those already simulated, in batches of 1,000. We note that the training of the autoencoder took less than 1 hour on a normal CPU, and we spent no effort on optimizing this. This could probably be reduced significantly, but in an executing project would be negligible anyway. For the random ordering, we in fact chose the best of 10 random orderings to make sure we weren't working with an unlucky outlier. Here is a summary of our experimental results. For any ordering of tests done without prior knowledge of the coverage of each test, we would expect to see the coverage closure follow a logistic curve, starting with a steep increase in coverage and then increasing more gradually. For the random ordering, this is really quite pronounced. The first 80% of coverage is achieved with under 1,000 tests, but then the fall off is quite dramatic. This very long tail is representative of the coverage curve we see in an executing project with constrained random generation of tests. The tail of the coverage curve for the novelty ordering of tests does much better, achieving coverage with 60% fewer tests, all the way up to 99.5% coverage. This correlation between novelty and coverage was stronger than we had hoped, and actually persisted for longer than we had expected. Even after 99.5% coverage, when the test selection based on novelty had a much bigger pool of poorly performing tests to choose from, it continued to do almost as well as the random test selection, getting from 99.5% coverage to 99.95% coverage in around 26,000 tests, compared to 22,000 tests for the random selection. In an executing project, it is likely that you would start targeting missing coverage by hand-coding tests before this point, but these results suggest that the use of novelty, as well as reducing the number of tests needed to close coverage significantly, is not overly sensitive to the point where you stop using it for test selection. We finish with some conclusions and some ideas for future work. Firstly, we note that if our experimental results were replicated in the real verification of the RSPU, then introducing a test selector based on novelty detection would save over 1 million simulations and close coverage 3 months or more earlier. This is enough to convince us to introduce such a test selector for our next generation RSPU development. We're also looking to introduce a test selector based on novelty in the verification of other IPs with similarly decoupled verification environments. For example, in our microprocessor verification, the generation of an instruction stream with an ISG is decoupled from its simulation. Applying novelty detection to microprocessor verification presents some different challenges and may require, for example, the use of multiple autoencoders to identify novelty for different functions of the microprocessor. Our experiment was concerned with reducing coverage redundancy, but we suspect that many of the 2 million tests we simulate explore any of the same design space, irrespective of whether we have coverage coded for it or not. It may be that we would explore more design space with 1 million novel tests than with 2 million random tests. We have no strong evidence for this, but there are some ideas for exploring this possibility discussed in the paper. Finally, we note that coverage-driven verification has its limitations. For example, the definition of a coverage model is subjective, and its implementation may be error-prone. Novelty may provide an antidote to these problems. For example, it may be interesting to explore why a test that looks very novel is not hidden new coverage. Again, this is not work that we have done, but we'd be very interested in any results in this direction. So that's the end of the presentation. Thank you for listening, and now I'm open to any questions.